When observations exceed what it allows by a factor of 8, that is not just a discovery, that is a structural problem. And what comes next moves beyond just finding big things in space. The standard model of cosmology has a proper name. It is called lambda CDM. Lambda refers to dark energy. CDM stands for cold dark matter. Together, they form a framework that has been tested against real data across decades, and it has passed those tests repeatedly. Lambda CDM predicted the detailed pattern of temperature fluctuations in the CMB. When satellite missions finally mapped those fluctuations at high precision, the predictions held. The model predicted specific ratios of light elements produced in the first minutes after the Big Bang. Observations of hydrogen, helium, and lithium in ancient gas clouds matched those predictions almost exactly. The model predicted how galaxies would cluster at large scales. Survey after survey confirmed the basic shape of that clustering. These are not small victories. These are hard, precise predictions tested against hard data, and the model survived. Lambda CDM is not a rough sketch. It is a detailed, mathematically rigorous framework that has earned its place as the standard description of the universe. And sitting at its center, holding everything together, is the cosmological principle, the assumption that the universe is the same in all directions, at large scales, uniform, smooth. No special places, no giant features, no structure beyond a specific size. This assumption is not just philosophically appealing, it is what makes the equations of lambda CDM solvable. It is what lets physicists write equations that describe the whole universe as a single system. Without it, the math falls apart. You cannot describe a deeply non-uniform universe using those same tools. You need different tools entirely. So when you find 3 structures that violate the maximum size set by the cosmological principle, the consequences are not just about those 3 structures. They are about the scaffolding. If the cosmological principle is wrong, or even approximately wrong in a way that matters at these scales, then every measurement made from inside a non-uniform region becomes suspect. And here is where the KBC void comes back in. Earth sits inside one of the largest underdensities ever mapped. If that void is real, and evidence says it is, confirmed, then we are already inside a region where the universe is not representative of the average. Measurements made from inside a giant void may not be valid proxies for the universe as a whole. The Hubble tension, the cold spot, the giant arc, the Big Ring, the Hercules Corona Borealis Great Wall. These are not 5 separate problems filed in 5 separate folders. They may all be expressions of the same underlying issue, a universe that is less uniform than the standard model assumes. A foundation cracked in ways that only become visible when you zoom out far enough. The model's size limit is 1.2 billion light-years. The largest observed structure is 10 billion light-years. That is a factor of more than 8 separating prediction from observation. In physics, when your prediction and your data are separated by a factor of 8, you do not adjust the data, you question the model. And right now, the model has more questions attached to it than anyone expected. But there is one more piece of the standard model under pressure, one that is even harder to replace than the cosmological principle. And the biggest dataset in history is making it shake. Dark energy is the name physicists gave to whatever is causing the universe to expand faster and faster over time. It makes up roughly 68% of everything in the universe. It is not a particle. It is not a field you can measure directly. It is inferred from the way distant galaxies are moving away from each other at an accelerating rate. Something is pushing space apart. That something is dark energy. In the standard model, dark energy is encoded as a specific term in Einstein's equations called the cosmological constant, lambda. the same lambda in lambda CDM. It represents a fixed, unchanging energy density built into the fabric of space itself. It does not grow stronger over time. It does not weaken. It just is, a constant. That assumption, that dark energy is a constant, is threaded through decades of cosmological calculations, expansion histories, age estimates, the predicted fate of the universe. All of it assumes lambda does not change. In April 2025, a collaboration of researchers released results from the Dark Energy Spectroscopic Instrument. This was not a routine survey. The instrument measured the spectra of 18.7 million galaxies and quasars across a wide range of cosmic distances. That number is the largest spectroscopic sample ever assembled in the history of astronomy. The goal was to track how the universe has expanded at different points in its history by measuring the distribution of galaxies at different distances. And buried in that massive dataset was a signal theory, approaching evidence. Dark energy does not appear to be constant. Its strength seems to have changed over time. Specifically, it appears to be weakening. The energy pushing space apart has been slowly decreasing across cosmic history. Not dramatically, not obviously, but the signal is there. The statistical significance is between 2.6 and 3.9 sigma. In physics, 5 sigma is the standard threshold for a confirmed discovery. 2.6 to 3.9 sigma means the signal is real enough to take seriously, but not yet strong enough to call proven. It is evidence, strong evidence, not confirmation. But here is why it matters so much. If dark energy is evolving, then the cosmological constant is wrong, not slightly off, wrong in a fundamental way. The cosmological constant says the energy is fixed. If it is changing, it is not a constant. It is something else entirely, something the standard model does not have a description for. Every calculation that used lambda as a fixed value would need to be revisited. The predicted expansion history of the universe would change. The estimated ages of the oldest galaxies would shift. The calculated distances to objects used as cosmic landmarks would become uncertain, and those distances feed into the measurement of the Hubble constant, the same Hubble constant that already has a tension built into it, the same tension that has not resolved in 20 years of increasingly precise measurements. Dark energy weakening would not necessarily solve the Hubble tension, but it would mean that the tool physicists have been using to model the universe, the cosmological constant, is broken. And if that tool is broken, every answer it produced becomes a question again. The ground is shifting, and the deeper you go, the less solid it gets. Here is something strange. Go back to the voids. Voids are not just empty space. They are not passive holes sitting between the filaments and clusters that make up the cosmic web. They are dynamic. They behave. And the way they behave might be changing how we see the entire universe. In regions where matter clusters together densely, gravity is strong. All those galaxies pulling on each other slow down the local expansion of space. Dense regions grow, but they grow slower than the cosmic average. Gravity resists expansion. In voids, the opposite happens. Matter is scarce. Gravity is weak. There is almost nothing pulling on anything else. Without gravity holding things back, the expansion of space inside a void runs faster than the cosmic average. The expansion does not accelerate because dark energy is stronger there. It accelerates because there is nothing slowing it down. Now, consider the numbers. Voids make up more than 80% of the volume of the observable universe, confirmed. Filaments, walls, clusters, galaxies. All the dense, spectacular structures astronomers spend their careers studying. Those occupy less than 20% of total cosmic volume. The universe is, by volume, mostly empty. If expansion inside voids runs faster than average, and voids dominate the volume, then the average expansion rate across the whole universe is heavily weighted toward void physics. The overall measured expansion rate is being pulled upward by the dominant volume, which is empty. This creates an interesting possibility. Maybe dark energy is not doing most of the work we think it is. Maybe what looks like an accelerating expansion when you average across a universe dominated by voids is partly or wholly an artifact of empty space expanding faster than its surroundings. Maybe you do not need a mysterious constant energy built into space itself. Maybe you just need to account for where you are measuring from and what most of the universe's volume actually looks like. If dark energy is partly an effect of voids rather than a fundamental property of space, then the cosmological constant describes the wrong thing. And if the cosmological constant is wrong, lambda CDM is describing the wrong universe. This is still theoretical theory. No one has produced a complete alternative model that passes all the tests lambda CDM has passed. But the idea is being taken seriously in the literature as a legitimate alternative that deserves investigation. And the KBC void is relevant here again. If Earth is inside a large underdense region, then every local expansion measurement has been made from inside a region that expands faster than the cosmic average. Every data point suggesting the universe expands faster nearby than the CMB predicts has been recorded from inside a void that may naturally expand faster than average, without requiring dark energy to explain the difference. Voids were supposed to be the background, the empty setting around the interesting structures, the white space on the cosmic map. They may be the engine, the thing actively shaping the expansion of the universe, not just the absence left behind by everything else. And if that is true, the way physicists have been modeling space for decades needs to be rebuilt from a different starting point. A starting point that takes time itself more seriously than current models do. There is a physicist in New Zealand named David Wiltshire. He has spent years working on a cosmological model that does not get as much attention as it deserves. The model is called timescape cosmology, and its central claim is both elegant and deeply unsettling. The claim is this: we have been treating time as uniform, as a single clock ticking at the same rate everywhere in the universe. And that assumption is wrong. Einstein's general relativity, the same theory that correctly predicts black holes, gravitational waves, and the bending of light around massive objects, tells us that clocks do not all tick at the same rate. Gravity warps space-time. In a region with strong gravity, where mass is dense and space is curved, clocks run slower. A clock sitting at the surface of a neutron star ticks at a different rate than a clock floating in open space. This is not a theoretical quirk. It has been measured in real experiments. It is why GPS satellites have to correct for the difference in clock rate between their orbital altitude and the surface below. Now apply that to the universe as a whole. In the dense regions of the cosmic web, the great clusters of galaxies, the filaments where matter piles up, gravity is strong, space-time is curved, clocks run slower. In the voids, the enormous near-empty regions that make up most of the universe's volume, gravity is weak, space-time is flatter, clocks run faster. Wiltshire calculated that clocks inside voids run approximately 35% faster than clocks in dense regions. Theory. That is not a small difference. That is a substantial difference in the rate at which time passes depending on where in the universe you happen to be. The standard model of cosmology does not account for this. It takes a mathematical average over all regions and assumes a single universal time. This works well enough when the universe is roughly uniform. But as structures grow and voids deepen across cosmic history, the difference between clock rates in dense regions and clock rates in voids grows larger. The universe becomes increasingly non-uniform, The single clock assumption becomes increasingly wrong. Timescape cosmology tracks each region's own local time. It does not average. It keeps the accounting honest. And here is what that produces. An observer sitting inside a void, where clocks run fast, would measure a higher expansion rate for the universe. Their clock ticks faster. The same physical expansion of space happens everywhere, but the fast clock records more time passing per unit of expansion. The expansion looks faster than it actually is from that reference frame. Earth sits inside the KBC void. Confirmed. We are measuring the expansion of the universe from inside a region where gravity is weak and clocks run fast relative to the cosmic average. If Wiltshire is right, the Hubble tension does not require a new physical force. It does not require dark energy to be wrong. It requires us to account for the fact that we have been measuring the universe with a fast clock and comparing those measurements to a very different era of cosmic history. That is a beautiful solution, clean, built on known physics, no exotic particles, no unknown forces, but beauty in physics is not evidence. And the next question Timescape cosmology had to face was uncomfortable. Timescape cosmology is, on its face, a remarkably clean proposal. It uses general relativity, a theory physicists have trusted for over a century. It requires no new particles, no new forces, no exotic modifications to how gravity works. It takes a known effect, the different ticking rates of clocks in different gravitational environments, and asks whether that effect has been properly accounted for in cosmological measurements. The answer Wiltshire proposes is no. It has not been accounted for, and that missing accounting is what produces the Hubble tension. But then comes the uncomfortable question, and it is a good one. The measurement of the Hubble constant from the CMB, the value of 67 kilometers per second per megaparsec that comes from Planck satellite data, was not made by looking at nearby galaxies. It was made by analyzing the pattern of temperature fluctuations in the cosmic microwave background radiation. That radiation is a snapshot of the universe from approximately 380,000 years after the Big Bang. Long before atoms fully formed, before galaxies existed, before any large-scale structure had taken shape, before voids existed in any meaningful sense. At 380,000 years old, the universe was nearly smooth. There were no galaxy clusters. There were no voids. There were only the very faint seeds of what would eventually become all of those things. The universe was so uniform that the clock rate differences Wiltshire describes were essentially zero. Matter had not yet separated into dense clumps and vast, empty regions. Everything was close to the same gravitational density. The timescape effect builds up over time, over billions of years of structure formation. As galaxies pull together and voids grow, the clock rate difference between dense regions and empty ones grows larger. It accumulates across most of cosmic history. It is not present at 380,000 years. So the CMB value of 67 should not be affected by timescape at all. The void clocks had not yet diverged from the dense region clocks when that snapshot was taken. This is where critics push back hard. If the local measurement of 73 is inflated because we are measuring from inside a fast-ticking void, and if the CMB measurement of 67 is unaffected by void clocks because it comes from an era before voids formed, then the two numbers should arrive at different values for entirely separate reasons. But the CMB number is the lower one. If void clocks inflate our local measurement upward, why is the CMB measurement lower at all? Why is it not simply sitting in the middle somewhere, representing the true cosmic average? Critics say timescape shifts the accounting of the tension rather than resolving it. The predictions do not perfectly align with what the CMB actually shows, and that gap is not small enough to ignore. Wiltshire and his collaborators have responses to these criticisms. The debate is ongoing. New data from larger surveys is being applied to the timescape predictions. Some researchers find the model promising, others find it incomplete. The tension is real. The clock idea is serious. It uses known physics and asks a precise question, and after 2 decades of searching, no one has closed the case. The universe is keeping its secrets, but the questions are finally sharp enough that the answers, when they come, will not be small. The universe builds structure through gravity. It has been doing this for nearly 14 billion years. Tiny regions that were slightly denser than average pulled in matter. Slightly emptier regions shed it. Over time, the denser spots became filaments and walls. The emptier spots became voids. This process is well understood. Computer simulations can reproduce it in detail. The Millennium simulation, run in 2005, modeled over 10 billion virtual particles and produced a cosmic web that looks remarkably like the real one. Confirmed, Illustris TNG, a more recent project, improved on that. It tracked gas, dust, and star formation alongside dark matter, and the result still matched large-scale observations well. Confirmed. These simulations reliably generate voids. Most are tens of millions of light-years across. Some reach a few hundred million. The Boeter's void, at 330 million light-years, sits at the outer edge of what these simulations produce at the right frequency. It is unusual. But it is not impossible. The KBC void is a different conversation entirely. 2 billion light-years across, 20% less dense than the cosmic average. Confirmed. To generate a structure like that in a lambda CDM simulation, you need to run the simulation many times and get lucky, very lucky. Studies estimate that a void of KBC's scale and depth appears in roughly 1 in 10,000 simulation runs. Theory: 1 in 10,000. That is not a rare event in the way that a storm or an eclipse is rare. That is a near impossibility under the rules the model is supposed to follow. This is the problem. Lambda CDM was specifically designed to predict how structures form and how they are distributed, voids included. The Millennium simulation and Illustris TNG were built to test that predictive power, and they do well across most of the universe. The cosmic web they produce matches what telescopes see in most directions. But we live inside the KBC void. That is our home. And the model that works everywhere else puts the odds of our neighborhood existing at roughly 1 in 10,000. Think about what that means. If you ran the universe again from scratch, using the same physics and the same initial conditions, you would get our void roughly once in 10,000 tries. The model does not forbid it. Nothing is violated. But the model strongly implies that whatever region we ended up in should look more ordinary than this. It does not. The standard answer is that we got unlucky. Statistics allows for outliers. A 1 in 10,000 event is not the same as an impossible one. But here is what makes cosmologists uncomfortable. The KBC void is not the only anomaly. It is not the only thing our model assigns low probability to. The Hubble tension is low probability. The cold spot in the cosmic microwave background is low probability. The large-scale structures we have been mapping are, individually and collectively, low probability. At some point, accumulating low probability events stops being a coincidence. At some point, the model is not generating unlikely predictions. The model is wrong. Theory. The simulations were supposed to confirm the standard picture. For most of the universe, they do. For the region we actually live in, they are struggling to keep up. Let's go back inside the Boeter's void, not to the edge, where empty space meets the first dim walls of distant galaxies, all the way inside, to the center. For years after the 1981 discovery, astronomers assumed the interior was genuinely empty. That was the point. A void, nothing there. Then, Surveys improved, and something turned up. 60 galaxies, scattered through a region that should have had none, confirmed. At first, this seemed like good news for the standard model. Voids are not perfectly empty. A few galaxies surviving inside one made sense. Then someone looked more carefully at where those galaxies were sitting. They were not scattered randomly through the void interior. They were aligned, all 60 of them, arranged along a single structure running through the middle of the Deepens void. A filament, confirmed. A narrow thread of matter tracing a line through 330 million light-years of emptiness. That is strange. Very strange. In the standard picture of cosmic structure formation, filaments form at the boundaries between voids. They are the seams where matter from multiple directions has been pulled by gravity. They mark the edges where different regions of the cosmic web meet. A filament is, by definition, a place where matter concentrates. A void is, by definition, a place where matter drains away. These two things should not share the same address. A filament inside a void is a contradiction in terms, unless something unusual happened. Several ideas have been proposed. Theory. One is that the Deepens void is actually a cluster of smaller voids that merged over billions of years. When smaller voids collide and absorb each other, the walls between them can collapse inward and leave behind a filamentary leftover in the interior. The 60 galaxies could be leftovers from one of those old internal walls, now stranded in the middle. This is possible, and simulations can produce something like it, but nobody has confirmed that this is what happened in Deepens specifically. Unknown. A second idea is that the filament is the last surviving structure from a secondary process. Small-scale density fluctuations that got trapped inside the void before it fully evacuated and never had enough time or enough neighboring matter to disperse completely. Again, plausible. Again, unconfirmed. Unknown. What makes this genuinely uncomfortable is not just that the filament exists, it is what the filament's existence implies. Matter inside the Deepens void did not simply drain outward. Something kept some of it in place, organized it, threaded it into a structure. That requires either a mechanism we have identified and confirmed, or a mechanism we have not. Right now, it is the second one, unknown. The void has internal architecture that standard void formation theory does not fully explain. The filament is real, the galaxies are real, the alignment is too clean to be coincidence. But 44 years after discovery, no one has a confirmed account of how that filament got there and why it stayed. Here is the part that keeps pulling researchers back. If the Deepens void has internal structure we cannot explain, and if the KBC void at 2 billion light-years has properties that appear in 1 in 10,000 simulations, then the voids are not simply the absence of things. They may have their own physics, their own history, their own story. We have been treating them as blank space. They are not blank. There is a picture most people carry around in their heads about how galaxies work. Dense environments, rich clusters, galaxies packed close together. It pulls on each other, merging over billions of years. That is where the action is. That is where stars form. The picture is wrong. In 2005, astronomers studying void galaxies noticed something they did not expect. The galaxies inside voids were bluer than average. Confirmed. Blue light from a galaxy means young stars. Young stars mean active star formation. Active star formation means a galaxy is alive and growing, converting its gas into new stars at a high rate. The galaxies inside the emptiest regions of the universe were doing more of this than galaxies in dense clusters. More star formation in less matter. That was the result. It made no intuitive sense. The standard assumption had always been that dense environments drive star formation. More matter means more material for stars to form from. More gravitational interaction means more activity. The richest clusters should produce the most stars. The emptiest voids should produce the fewest. The data disagreed. Confirmed. The resolution turned out to be hiding inside what dense environments actually do to galaxies. When galaxies live in clusters, they are constantly interacting. Tidal forces from neighboring galaxies stretch and distort their disks. It pulls gas outward. Confirmed. When two galaxies merge, the collision disrupts the disk structure that allows steady, long-term star formation. When a galaxy passes through the hot gas that fills a cluster, ram pressure stripping tears away the cold gas supply. The galaxy needs to form stars. Confirmed. Dense environments are violent. And violence, it turns out, is bad for star formation. A void galaxy has none of these problems. It sits alone in 300 million light-years of empty space. Nothing is stripping its gas. Nothing is colliding with its disk. Nothing is disrupting its structure. It converts its gas into stars on its own schedule, steadily, without interruption, for billions of years. The isolation that looks like poverty is actually protection. This flips the original assumption completely. Dense environments were supposed to be the engines of the universe's star-forming activity. Void environments were supposed to be quiet and passive. The observations show the reverse. Confirmed. The richest star-forming galaxies may be sitting in the emptiest places, left alone long enough to do what they do without interference. There is a deeper implication here. If we built our model of galaxy evolution primarily by studying galaxies in dense environments, and most of our early, detailed galaxy surveys were concentrated in rich clusters because that is where many galaxies were easy to find, then we may have been learning from the exception rather than the rule. Void galaxies are numerous. They cover a large fraction of the universe's volume. A model of galaxy evolution that gets void galaxies wrong is missing a large part of the full picture. And there is still one more thing. The void galaxies are younger. Their stellar populations, their chemical abundances, their structural properties all point to galaxies that are further behind in their development than comparable galaxies in denser regions. Confirmed. The universe's empty spaces are not done yet. They are still in progress. While the clusters have moved on, the voids are still doing their early work. That is not what the standard picture predicted. Here is a sentence that would have sounded absurd 20 years ago. Voids are now one of the most powerful measurement tools in cosmology. Not the galaxies inside them, not the walls around them, the voids themselves, the empty space. To understand how this is possible, you need to go back to the very early universe. In the first few 100,000 years after the Big Bang, the universe was a hot, dense plasma. Pressure waves moved through it. Sound waves, essentially, but moving through a medium of charged particles and light. These waves had a characteristic scale, a distance that the sound could travel before the plasma cooled and the waves froze in place. That scale is approximately 490 million light-years. Confirmed. It is called the Baryon Acoustic Oscillation Scale, and it left an imprint in the distribution of matter across the entire observable universe. Everywhere you look at separations close to 490 million light-years, galaxies are slightly more likely to be found together. The signal is subtle. You need to map millions of galaxies to detect it. But it is there, stamped into the large-scale structure of the cosmos like a watermark. Cosmologists use this scale as a ruler. Because the scale is set by physics we understand well, we can calculate what it should be. Then we measure what it actually is in the galaxy maps. The ratio between the two tells us about the geometry of the universe, the expansion history, and the nature of dark energy. Confirmed. Now here is where voids come in. The Baryon Acoustic Oscillation Scale should be the same everywhere. It is a property of the early universe, set before structure formation began. If you measure it in dense environments, you should get the same answer as when you measure it in void environments. If you do not get the same answer, that is telling you something profound. The local universe and the average universe are not the same. The local universe is not a representative sample of what the full cosmos looks like. Theory. This is the test. Compare the acoustic scale in regions of different density. If it matches everywhere, the universe is statistically uniform at large scales. If it does not match, the cosmological principle, the assumption that the universe looks the same everywhere at large enough scales, is in trouble. To run this test well, you need enormous samples. The old surveys did not have enough galaxies to make the comparison precise. The statistics were too noisy. You could not cleanly separate the void measurement from the dense measurement and compare them with confidence. Then came the dark energy spectroscopic instrument, 18.7 million galaxy redshifts. Confirmed. A sample large enough to slice the universe by environment and still have enough galaxies in each slice to detect the acoustic scale with real precision. The test that could not be run cleanly before is now runnable. The results of this specific comparison are still being analyzed. The measurement of whether the acoustic scale differs between void regions and dense regions has not yielded a definitive answer yet. Unknown, but the fact that it can now be asked rigorously with actual data instead of theoretical projections changes the nature of the investigation. For the first time, astronomers have a sharp enough instrument to test whether the universe is truly uniform at large scales, or whether the emptiness has been hiding a deeper difference all along. The dark energy spectroscopic instrument does not just map where galaxies are right now, it maps where they were across deep time. Because light takes time to travel, looking out in distance is the same as looking back in time. A galaxy billions of light years away is being seen as it existed billions of years ago. By mapping millions of galaxies across a wide range of distances, the instrument can reconstruct not just the current structure of the universe, but its history. How fast it was expanding at different points in the past. How dark energy behaved as the universe aged. This is the core mission. And in 2025, the first major results arrived. The picture they painted was not what the standard model predicted. Dark energy, in the lambda CDM model, is represented by a cosmological constant, a fixed, unchanging energy density built into the fabric of space. It does not vary with time. It does not strengthen or weaken as the universe ages. It just sits there, always the same. That is what the constant means. Confirmed. That was the assumption built into the model in the late 1990s, when observations of distant supernovae first revealed that the universe's expansion was accelerating. The DESI data suggests dark energy was not constant. Theory. When researchers reconstructed dark energy's strength across different epochs, using the baryon acoustic oscillation scale as a ruler at different distances, they found a pattern. Dark energy appeared stronger in the past. It appears weaker now, decaying, not constant. The acceleration of cosmic expansion may itself be slowing down. Theory. The statistical significance sits between 2.6 and 3.9 sigma, depending on how the data is analyzed and which external datasets are combined. Confirmed. That is substantial evidence, but it falls short of the 5 sigma threshold that physicists use as the standard for a confirmed discovery. It is not proof, it is a strong signal that could still be noise, or it could be pointing at something real. If it is real, the implications are large. A cosmological constant is just that, a constant. If dark energy is not constant, then the constant has to go, and the constant is not a small piece of the model. It is embedded in every cosmological calculation that depends on the expansion history of the universe, the age of the universe, the distance to every galaxy, the interpretation of every supernova measurement, every structure formation calculation that depends on how long dark energy has been operating at what strength. If dark energy changes over time, all of these need to be revisited. Theory. Every number that assumed a constant gets a new uncertainty attached to it. The calibration work that took decades could need to be redone. There is also a more complicated possibility. A decaying dark energy could close some of the gap in the Hubble tension. The numbers from the early universe and the numbers from the local universe might disagree, partly because dark energy was stronger in the past and weaker now, and the calibration assumed it was constant throughout. If true, that would be some relief. But it could also open new inconsistencies that have not been noticed yet. Unknown. The history of this field is full of apparent solutions that generated harder problems than the ones they solved. The DESI result is not the end of something. It is the beginning of a harder question. When a model fails, you replace it. That is how science is supposed to work. The problem is what happens when you try to replace lambda CDM and nothing fits. Several alternatives have been developed. Each one addresses some of the failures of the standard model. Each one introduces its own complications. Quintessence is one of the oldest proposals, theory. Instead of a cosmological constant built into the structure of space-time, quintessence treats dark energy as a dynamic field. A field with a value that changes over time, rolling slowly down a potential energy curve, weakening as the universe ages. This would naturally explain the DESI result. A decaying dark energy field is exactly what quintessence predicts, but quintessence has its own problems. It requires a field whose current energy density is extraordinarily small compared to what particle physics predicts it should be. Getting the numbers to work requires fine-tuning, and quintessence does not, on its own, resolve the Hubble tension or explain the large-scale structures. Interacting dark energy goes further. Theory. In this framework, dark energy and dark matter are not completely separate. They exchange energy. Dark matter slowly transfers energy to dark energy or vice versa, changing the expansion history in ways that a pure cosmological constant cannot. Some versions of interacting dark energy can reduce the Hubble tension, but adding an interaction requires adding parameters. And with enough free parameters, you can fit almost anything. Fitting data is different from explaining it. Modified gravity takes a different approach entirely. Theory. Instead of changing what dark energy is, it changes how gravity works on large scales. General relativity is spectacularly confirmed at small scales. Solar system tests, pulsar timing, gravitational wave observations all agree with it. But on cosmological scales, billions of light years across, we have never tested it directly. Modified gravity theories propose that the relationship between matter and space-time geometry is different at those scales. This could explain large-scale structure anomalies and possibly the Hubble tension. None of these work across the full dataset. Confirmed, when you ask any of these alternatives to simultaneously fit the cosmic microwave background power spectrum, the locally measured Hubble constant, the large-scale structures that exceed standard predictions, and the DESI dark energy evolution, they fail in at least one area. Quintessence struggles with the Hubble tension. Interacting dark energy fits the tension but strains the microwave background fits. Modified gravity models can handle large structures but often break something else. There is no replacement on the table right now that cosmologists agree on. Lambda CDM, for all its accumulating failures, still fits more data simultaneously than any of its proposed replacements. Confirmed. That is why it has not been discarded. Not because cosmologists think it is right, because they do not have something better to point to yet. The field has identified the failures. It has generated alternatives. It cannot agree on which alternative is correct, and none of the alternatives is actually better across the board. The model is wrong. The replacement has not arrived. The investigation is running on an incomplete map of territory that keeps revealing new edges. There is a problem that runs deeper than any single measurement. It has been building quietly for years, and it changes the way every anomaly we have discussed should be understood. Every number in cosmology is anchored to something local. The Hubble constant, the rate at which the universe expands, is measured by observing nearby objects first. Cepheid variable stars in nearby galaxies. Type Ia, supernovae in galaxies slightly farther away. Each rung of the distance ladder is calibrated against the one below it. Confirmed, the whole structure rests on the base, and the base is here, in our neighborhood, inside the KBC void. The matter density of the universe is measured from surveys of nearby large-scale structure. Those surveys are done from here. The age of the universe is derived from the Hubble constant combined with other parameters, all of which flow from measurements made here. Even the interpretation of the cosmic microwave background depends on assumptions about local physics that are calibrated locally. The KBC void is roughly 20% less dense than the cosmic average over a region 2 billion light-years across. Confirmed, that underdensity is not uniform. The void has a bulk flow, a large-scale streaming motion of galaxies moving outward from the void center toward the surrounding denser walls. That bulk flow adds a small but real velocity component to every galaxy in the local universe, on top of its cosmological recession velocity. Confirmed. When astronomers measure the recession velocity of a nearby galaxy and use it to infer distance and expansion rate, they are looking at a signal that has that bulk flow component folded in. If the bulk flow is not fully accounted for, the inferred Hubble constant comes out slightly higher than the true cosmic average. Theory. Not by a lot, but by enough to matter. How much? Some estimates suggest the KBC void's bulk flow could account for a meaningful portion of the discrepancy between the local and early universe Hubble constant measurements. Theory. The full tension is around 5 to 8 kilometers per second per megaparsec, depending on the dataset. The void may not explain all of it. It might explain a significant share, unknown. But here is the deeper point. It is not just the Hubble constant. Any measurement anchored to nearby objects and then extrapolated to universal scales carries this risk. If the local universe is systematically different from the average universe, and the KBC void is direct evidence that it is, then the calibration chain at the base of all cosmology is sitting in an anomaly. This is not a small concern. The entire framework of precision cosmology assumes that our measurements here are representative of measurements anywhere. Confirmed as assumption, magnitude of bias, unknown. That assumption has never been rigorously tested against the possibility that we are inside a 2 billion light-year void. The void was identified in 2013. The implications for the measurement chain have been discussed since then. A full, confirmed correction has not been applied to the standard cosmological parameters. Unknown. We are still working from numbers whose foundation may be skewed. Everything built on top of a biased foundation inherits the bias. 1981. Robert Kirshner and his team find a gap, 330 million light-years of near-empty space in the direction of the Boötes constellation. They publish, the field is startled, and then the long work begins. 44 years have passed. In that time, cosmology has transformed. Satellites have mapped the cosmic microwave background in extraordinary detail. Ground-based surveys have catalogued hundreds of millions of galaxies. Supercomputers have simulated the full history of cosmic structure formation. Gravitational wave detectors have confirmed general relativity in extreme conditions. Confirmed. The precision of cosmological measurement has advanced by orders of magnitude. And yet, the Deepens void still does not have a confirmed explanation. The basic question is the same one Kirshner's team was asking in 1981. How did 330 million light-years of space become nearly empty? What process removed the matter? What timeline does it fit into? Standard simulations can generate a void of Deepens' size, but not at the frequency that would make it an expected feature of the universe. It sits at the edge of what is plausible. Confirmed. Not impossible, just improbable. Two main mechanisms have been proposed. The first is a chain of merging voids. Smaller voids form early, and as they grow and expand, their walls approach each other and merge. This creates a larger, combined void. Repeat this process enough times, and a 330 million light-year void emerges. Computer models can produce this outcome, but nobody has confirmed observationally that this is how the Deepens void specifically formed. The signature of sequential merging, the geometry of the walls, the velocity fields around the void, has not been cleanly identified in the Deepens data. Unknown. The second proposal is a primordial density fluctuation, a region that was already below average density in the very early universe, possibly seeded by processes in the first moments after the Big Bang, that simply expanded and deepened over time. This is possible. The problem is that a fluctuation large enough to produce Deepens would itself be unusual. Unusual enough that it circles back to the same statistical problem. Theory. Inside the void, the filament of 60 galaxies remains unexplained in detail. Unknown. The models that could produce it are plausible. None has been confirmed as the actual mechanism. And there is one more puzzle that rarely gets mentioned in summary accounts. Some of the galaxies inside the Deepens void show high excitation emission spectra. Confirmed. Their gas is being excited at higher energy levels than you would expect in a quiet void environment. The energy source for that excitation has not been identified. Unknown. This is what 44 years of investigation looks like. A case that keeps generating new questions faster than old ones get answered. The void is still there, exactly where Kirshner's team found it. Still 330 million light-years of near-empty space. Still internally structured in ways that standard theory does not fully account for. Still home to galaxies doing things nobody has explained. The longest-running open case in extragalactic astronomy. And it is still open. Look at the sequence of what has been found. 1981. Deepens void. 330 million light-years. A gap that challenged the models of its time and forced astronomers to take large-scale emptiness seriously. 2013. KBC void. 2 billion light-years. A structure so large that the Deepens void fits inside it many times over. We are inside it. It appears in roughly 1 in 10,000 standard model simulations. Confirmed. 2015. Eridanus supervoid. 1.8 billion light-years. The best candidate explanation for the cold spot in the cosmic microwave background. A bruise of slightly lower temperature in the oldest light we can see. Large enough that photons passing through it lose energy in measurable ways. Confirmed. 2021. The giant arc. 3.3 billion light-years. A curved structure of galaxies and clusters stretching across a third of the observable universe at a single redshift. Confirmed. Under the cosmological principle, it should not exist. 2024. The Big Ring. 1.3 billion light-years. A near-perfect ring of galaxies discovered in the same survey region as the giant arc, at nearly the same distance. Two structures in the same patch of sky, both exceeding the theoretical scale limit, both found within a few years of each other. And then, beyond all of these, the Hercules Corona Borealis Great Wall, estimated at 10 billion light-years from end to end. Theory, boundaries, still being mapped. Larger than any structure the standard model can generate at any point in cosmic history. Each new structure is larger than the one before it. Each one exceeds the theoretical limit by a greater margin. The theoretical limit itself was supposed to be the scale at which the universe becomes smooth, roughly 300 million light-years. Every structure on this list is larger than that. Most are larger by an order of magnitude or more. This is not a collection of separate surprises. Look at the pattern. Every time a more powerful survey covers a larger volume of space, it finds structures that the previous model said should not be there. The structures do not stop at the edge of each new survey. They keep going. Each boundary reached turns out to be not a boundary at all, but the edge of what the instruments could see at that moment. Unknown. The cosmological principle says the universe becomes uniform at large enough scales. It is not a derived result. It is an assumption. It was built into the foundation of the standard model because it simplifies the mathematics enormously and because early surveys seemed consistent with it. It was never confirmed at the scales we are now reaching. At the scales we are now reaching, the universe is not uniform, confirmed for the structures listed above. It has structure at every scale we have mapped, and every time we map a larger scale, we find structure there too. That is not an anomaly. It is a trend that has no observed endpoint. The universe may not have a scale at which it becomes the smooth, featureless background the models require. Every horizon we have pushed through has revealed something the model did not predict. The next horizon is already being drawn. In 1981, a team looked at a region of the sky and found almost nothing. No galaxies, no clusters, no walls, just space. A void hundreds of millions of light-years across, where the model said there should be structure. They asked a simple question: why is this here? 44 years later, the investigation has not answered that question. It has made it bigger. The gap is no longer 330 million light-years. It is 2 billion, and we are inside it. Every star visible to the unaided eye, every galaxy we have catalogued, every telescope we have built and aimed at the sky, all of it lives inside a region that is 20% emptier than the cosmic average, and that appears in roughly 1 in 10,000 simulations of the universe. Confirmed theory. The expansion rate of the universe, measured locally and measured from the early universe, disagrees by a margin that 5 sigma of statistical confidence cannot bridge. The disagreement has not narrowed as instruments improved. It has held firm and grown sharper as a genuine conflict. Confirmed. The oldest light in the universe has a cold bruise, a region where the temperature is slightly lower than it should be, extending across an angular patch large enough to require an explanation. The leading candidate is a void 1.8 billion light-years across that the light passed through on its way to us. Confirmed as a structure, not confirmed as the full cause. Confirmed, unknown. The universe built structures that should not have had time to form. A ring 1.3 billion light-years across. An arc 3.3 billion light-years long. A wall 10 billion light-years from end to end. Each one sitting outside the boundary that the standard model draws around what is physically possible given the age of the universe. Confirmed for some, theory for others. Dark energy may be changing. The energy driving the accelerating expansion of everything may have been stronger in the past and weaker now. This means the constant was never really a constant, failing not just in theory, but in observation. Theory, 2.6 to 3.9 sigma. The measurement chain that anchors all of cosmology. Every Hubble constant, every age estimate, every distance measurement runs through the local universe. The local universe is an anomaly. every number downstream of that anchor carries an uncertainty that has not been fully propagated through to the final results. Theory. The model is accumulating failures. Not one, not two. Failures at every scale, in every type of observation, from the oldest light to the newest galaxy surveys. The gap Kirshner's team found in 1981 was a hole in the data, a place where observations showed less than expected. The gap in 2025 is a hole in the model, a place where the framework itself does not describe what the observations are showing. The next generation of instruments is already being built and launched,